Hello, civil engineers. Welcome back to the lecture. In this lecture, we will see why is that we are using a steel and the concrete as a reinforcement only. Why is that only the steel is being used? Why don't we use any other material? And also in the previous lecture, if you are just concentrated on my lecture, I told you that cement is a binder, isn't it? But what exactly makes cement is a binder? That is a main question, right? There should be something in the cement. You can see the cement here. There should be something in the cement which actually makes it act like a binder. We'll try to understand that, right? So for that, there's a concrete technology course of mine on the same Udemy platform. If you are interested to learn all that thing, you can buy the course. So let me not get completely into that, but I'll give a certain, basic idea what exactly I want to tell about the binder. So see, when we prepare the cement, right? Because cement you have to manufacture. So when you prepare the cement, you have two ways. Either you can do with the help of a dry mixing or a wet mixing. So wet mixing, we don't use it. We usually make cement with the help of a dry method. So, and this is how that dry method is made and all. I'll not explain it here. It's already explained in one of my concrete technology course, but I'll give you an idea. Okay, this is how the dry method is done, and it's a modern and a widely used method. Whereas the wet mix, no, we don't use it anymore. And why we don't use it anymore? There are certain reasons behind that. Because the fuel consumption is more and all. So that is why we don't use the wet method. Now, when you prepare the cement, right, there are certain compounds which will come once the cement is manufactured. What I'm trying to tell is, see, so this is how the cement is manufactured. Once you manufacture the cement and you have a cement with you, in that cement there are certain compounds which are called as Box compound. So you can see it here. Box have written it here. So Box was the person who identified these compounds. And which are those compounds? So it is one is C3S, the other is C2S, the other is C3A. Then we have C4AF. What is this C3S? C3S stand for tricalcium silicate. C2S stand for dicalcium silicate. C3A stand for tricalcium aluminate, and C4AF stand for tetracalcium aluminoferrate. And these are the percentage, by how much percentage they are present in the cement. Like C3S, we have 30 to 50% in the cement. C2S, it occupies 20 to 45% in the cement. C3A, it occupies 8 to 12%. C4AF, it occupies 6 to 10%. So based on the types of a cement, like we have rapid hardening cement, we have slow setting cement, we have extra rapid hardening cement. So based on the cement, we try to proportionate this, right? So that is how we do. Again, all those things, it is explained there. Now, why did I come to this particular slide is that how that binding property will come. So this C3S and C2S, no, when they react with water, like I say, I have a cement here, right? Now I'm going to say I have water, I'm going to pour the water. So the moment I pour the water in this, so the hydration is going to happen. That means there's a chemical action happening between the cement particles and the water. So because of that, what will happen? Because of that, this C3S and C2S compound, no, they'll react with water. So I'll show you what exactly I want to tell. Yeah. Yeah. So this C3S, it's called tricalcium silicate, right? So the C3S, you can see it here, it will react with water and it's going to form CSH gel. So this CSH gel is called as taubermorite gel. Okay. And this gel itself will act as a binder. So that is why I told cement is a binder. So who is actually responsible? This particular compound called as C3S, when it reacts with water, it will form CSH gel, and that CSH gel will have that binding property in it. So because of that reason, no, we call cement as a binder. That's C3S. And in the same way, there's one more compound which is called a C2S, that is dicalcium silicate. Even the dicalcium silicate will react with water. Again, the CSH gel is formed. So because of this reason, we get that binding action, right? So again, there's a lot of things you need to understand. I've given a small overview, but exactly how is that the word binder is all about. So because of this taubermorite gel, no, so we'll go back to that. So this is a taubermorite gel, and because of that gel, the binding action is formed. Again, there are many things that you need to understand, which we are not going to take up in this particular course. You can learn from there, right? So we'll go back to the main agenda again. Now again, so I hope that is why I used the word, it is a binder here. And why is that binder? Because of C3S and C2S, which will give the binding action to the cement. And that is why it can hold any material. When you put cement, coarse aggregate, fine aggregate, you're going to get that hard mass, and that binding action is because of this particular C3S and C2S. Yeah. Now we'll go to the most interesting part. Now I took rebar, isn't it? Directly I showed you rebar. Why is that? where we are using only steel. Why not the other components? I mean, why not the other materials like we have bronze, we have gold, we have silver and all? Why don't we use those materials, and why we go with only steel? So we'll try to see the reason behind that. So there's something called coefficient of thermal expansion of steel and concrete is almost same and nearby values. What is trying to tell? Suppose let me consider this as my concrete. Okay, let me consider this as my concrete. Now the room temperature is 27 degrees Celsius for me. Let us say I'm going to increase the temperature. Instead of 27 degrees Celsius, I'll make the temperature of this room to 35 degrees Celsius. Since there's a change in the temperature, this particular concrete is going to expand. So initially it was of this length. Okay, you can see the length. Initially this is of this much length. Let us say due to increase in the temperature, even the materials are going to expand. So here what will happen? Let us say this is going to expand by 5 mm. So if you don't understand in mm, we'll speak in terms of centimeter. Let us say it's going to increase by 50 centimeter when I'm increasing the temperature. In the same way, right now the room temperature is 27 degrees Celsius. Let us say I'm completely cooling down my room, and I'll bring the temperature somewhere close to 18 or let us say 15 degrees Celsius. Since there is decrease in the temperature, this particular concrete it's going to shrink. So originally this was the length. Now due to the shrinkage, let us say it has got shrink by let us say 20 centimeter. So what is happening? If I'm increasing the temperature, it is increasing, that is there's an elongation, and if there is a decrease in the temperature, it is going to shrink. So this is how the concrete is going to behave. In the same way, if I take a steel, even now let us say I'm increasing temperature again. Now again the steel is also, if I increase the temperature from 27 degrees Celsius to let us say 35 degrees Celsius, like I did it for the concrete, even the steel is going to expand. Let us say even the steel is also going to expand by let us say 45 to 46 centimeter. Concrete was expanding by 50 centimeter. Let us say this is expanding by 45 centimeter. In the same way, if I decrease the temperature of the room, and if I bring it down to 15 to let us say 18 degrees Celsius from 27 degrees Celsius, even this is going to shrink. And let us say it will shrink by let us say some 20 centimeter, or let us say 25 centimeter. Concrete was shrinking by 20 centimeter, whereas steel is going to shrink by 20 centimeter. Concrete is 25, this is 20, right? So both the materials are going to expand and shrink. Now what will happen if you make a combination of this both? That is, a concrete is one material, steel is other material. Now if there is an increase in the temperature, what will happen? Concrete is going to shrink. Sorry, if there is increase in the temperature, concrete is going to increase, elongation is going to happen. Even in the steel is elongation is going to happen. So in between them, what will happen? That proper bonding will not be there. But one advantage what we have is there's something called coefficient of thermal expansion. So that means if you look here, the steel, it has got 1.1 into 10 to the power of minus 5, whereas concrete has got 1.2 into 10 to the power of minus 5. So the coefficient of thermal expansion between the steel and the concrete is almost same. So that means even there is increase in the temperature, concrete and steel both will be held together, and there is no much variation between them. Let us say my concrete got expanded by 50 centimeter. This steel will get expanded by 45 centimeter. There's no huge difference. Like concrete let us say got expanded by 50 centimeter, and if steel get expanded by 20 centimeter, there's a huge difference between 20 to 50. But 45 to 50 is not a huge variation, right? So there's even though there is an increase in the temperature, the bonding is good. In the same way, when there's a decrease in the temperature, concrete got shrink by 25 centimeter, whereas steel got shrink by 20 centimeter. That difference what we have from 25 to 20, it's not a huge difference. So again, even though there's a decrease in the temperature, there will be a good bonding between them. That is the reason we go with the concrete and steel as a RCC member and not with other material. In other material, what will happen? Let us consider, I'm taking gold for example. So in gold, what will happen? Maybe like I mentioned, concrete got expanded by 50 centimeter. Maybe gold will get elongated by only 10 centimeter. From 50 to 10, there's a huge difference, right? In the same way, if there is a decrease in the temperature, my concrete got shrink by 25 centimeter, whereas gold will get shrink only by let us say 2 centimeter. Again, from 25 to 2, there's a huge variation. Then what will happen if you make gold and concrete has a reinforcement? Let us consider. Of course, it's quite costly. Let us consider. Then what will happen? There won't be a good bonding between them. The moment you increase the temperature, concrete will try to go this way. It want to expand by 25 centimeter, whereas this gold will not allow because it will expand only by let us say 5 centimeter. So again, what will happen? There won't be a good bonding. So as a result of that, there's a cracks and all. So that is why I don't want that to happen. That is why most of the RCC structure we use steel as an reinforcement and not the any other material. What is the main reason behind that? There's something called coefficient of thermal expansion. You see here 1.1 and 1.2. There's no much huge variation, right? So that is why that's the main idea behind that. There's a one reason. Second is concrete is weak in tension. We know that, and it is strong in compression. Whereas steel, it is strong in compression tension. Both it is strong. Whereas concrete, it is weak in tension, but it is strong in compression. Again, this is the second reason we make a combination, because concrete cannot take tension. It will give up. It cannot take tension. So somebody has to come and save the concrete. So steel will come like a hero, and that is how their bonding is going to happen. So one will take concrete, the concrete will take the compression, and the steel is going to take the tension. Of course, steel will take your compression, but that is not what it is meant for. The concrete will take care of that. That's the second reason. Third, the bond between the concrete and the steel becomes strong due to the ribs present on the rebar. That means if you look to the rebar, if you look into the rebar, you can see a small ribs here, right? See, it's a kind of a ribs here. So this ribs, since it is rough in surface, and concrete, once it start to get coated on the surface of a rebar, there's a good bonding between them, and it's very difficult for you to pull it out because of the ribs present here. So that is the third reason why there is a good bond between the concrete and the steel. The next is the steel being ductile in nature makes it a perfect combination with the concrete, and hence steel is widely used material along with the concrete. Again, we know that this steel is very ductile in nature, isn't it? So moment if you pull, it will break, but it's going to elongate, and you're going to get that warning. So again, that is another reason why we take steel and the concrete as a combination, right? So all these were the fundamentals where we wanted to know what is the reason behind all these things, and why we should make use of steel and concrete as a reinforcement, or why do we use them as a RCC member, right? So in the next lecture, we'll try to understand what are the different types of cement, different diameters of the rebar, and all those things in the next lecture. So we'll see you back in the next lecture. Thank you.